Video, I'll be going over voltage and current division. And we'll start off by just trying to understand conceptually what is voltage and what is current. Because, you know, it might seem, trivial to you, but this is, I think, something a lot of students struggle with conceptually. I know certainly I did. And let's just go through it and clarify it right now. So you may have heard that voltage is an electric potential difference. But, what does that exactly mean? Why are we talking about potentials here? What significance does the word potential have in this sort of definition? And why is it a difference between what and what? Why are we talking about differences? So, first of all, just to get a big picture idea, you might have seen something like this. So here the voltage is sort of like the electromotive force. It's pushing the charge through the circuit, and the amps are like how much charge is being pushed through the circuit. And then the resistance, it's here. He has a tight grip on the charge here, and he's trying to basically resist the flow of current through the circuit, right? And this is okay for getting maybe a big picture idea of what's going on, but I don't really love this analogy because it doesn't really help our intuition too much. Let's get into what I think is a much better analogy, and this is the classic analogy for understanding circuits. We're going to take this electric circuit and we're going to model it as we're going to model it mechanically as basically a pipe, okay? So instead of water, instead of electricity flowing through the circuit, we have at this point water flowing through the circuit, okay? And let's try to sort of explore this a little bit, right? So let's say we have a simple circuit, okay? So here we have our voltage source, here we have like a resistor, and that's our circuit, okay? So now let's say if we're going to imagine this simple circuit in mechanical terms as a pipe, well then, okay, we're going to imagine instead of electrons flowing through the pipe, we're going to imagine water flowing through the pipe, right? Water flowing like this, okay? So the water's flowing. At this point, the water goes down through the resistor, and then it's here, okay? And let's say that this pipe is standing vertically up at like a certain, so it has a certain height, okay? It has a certain height. If we're a water molecule and we're starting here, okay? We're starting here, we're going, and then we go, and then we're starting here, we're moving along the pipe, right? And at this point, you can see we have a certain potential energy because of the height of the circuit. We have a certain gravitational potential energy, okay? And that gravitational potential energy, as the water falls down through the pipe, it turns into kinetic energy, okay? So let me just make a note of that. We have gravitational potential energy, and then we have the potential energy goes to kinetic energy, okay? And then when we're down here, we have no more potential energy, okay? So a water molecule here, how is it gonna, go back up and go back down through the circuit? Well, we're gonna have to go through here, and we're gonna have to get pumped up, right? The water's gonna have to get pumped up back to that height, whatever that height was, maybe like 10 meters or something. Maybe it's like a height of 10 meters. So we're gonna have to get pumped back up, okay? So we can think of this voltage source as a pump, and the resistor can, it can be, maybe like a little, we can imagine it as some sort of like a fan or something. So the water's, turning the fan, it's turning, as the water flows down the pipe, it turns that potential energy that it has due to gravity into kinetic energy. So of course in electric circuits, it's exactly the same thing, right? These electrons have a certain electrical potential energy. They have a certain stored energy that they're able to convert into into energy through a load when they pass through a load, right? And the voltage, all it does is it supplies the electrons like that potential energy again. It brings them back up to that height so that they can go back down and do work through the load, okay? So I hope that sort of explains where the potential terms comes from. It literally means the same thing as gravitational potential. It's literally, you can think of it literally in the same way as you think of gravitational potential energy, right? It's just this stored energy you have in the field, and then you can release that stored energy to do work, right? Or to do something useful. So like you can release that energy through a resistor, and it basically just turns into heat. You can release it through a light bulb, and it turns into heat and light, and various other things, of course, depending on your load. So what do we mean by difference? Difference between what and what? So you guys may remember from high school doing from high school physics. There's no such thing as an absolute value for energy, right? We can only define energy in terms of energy differences, okay? And so when we say potential energy in a circuit, we mean for electric potential energy in a circuit, we're always measuring it with respect to a certain point that we define as ground, okay? And again, the great thing about ground is this, again, it's directly analogous to ground when you think about gravitational potential energy and in terms of gravity, okay? So let's say I'm a little guy, right? And I'm standing on I'm standing on what I think is the ground, okay? And I say, okay, well, if I have a ball that's 10 meters above this ground, and the ball, let's say it's a 1 kilogram ball, then the potential energy of this ball is equal to 1 kilogram times 9.8 meters per second squared times 10 meters, okay? So that's just mgh, right? That's the equation for gravitational potential energy, okay? And I'm like, okay, so this ball, I think it has this much potential energy, okay? That's what I think. Okay, but what about this guy who's, living all the way down here? Let's say, this is not to scale, but let's say he's living, there's a 20-meter difference between where I am and where he is, so I have the high ground in this case, and, maybe it's Obi-Wan and Anakin. So, I mean, this guy's all the way down here, and he thinks, well, he's like, well, compared to what I think is the ground, that ball has way more potential energy, right? That ball, it's, what he thinks is, let's say what he thinks is it's 1 kilogram, gravity is the same, but, now it's like 30 meters up, so it has way more potential energy from his point of view, okay? And as you can see, it's relative. There's no absolute potential energy value that the ball has. It's all relative to what whoever thinks is the ground. And basically, you can define the ground, and basically, it's the exact same thing in an electrical circuit. Okay, we're defining when we define voltage differences, we pick a certain voltage to be 0 volts. That doesn't mean that at that 0 volts the electron has no energy, and at the 0 volts it can't we can't use an electron that's that's at 0 volts. Okay, you can have like negative voltages, right? Like it's literally all just a matter of convention. Okay, so you could have 3 10-volt batteries connected to each other. Okay, or 5-volt batteries, 5 volts, 5 volts, 5 volts. Okay, and you could say, okay, well, or actually, let's make this a bit easier. 10 volts, 10 volts, 10 volts. And you could say, okay, well, if I pick this as 0 volts, right, just arbitrarily, then here we're going to have, here's going to be 20 volts, and here's going to be minus 10 volts, okay? I could, just because this is 0 volts doesn't mean there's no energy, there's no energy at this point in the circuit, right? There's obviously still, you can obviously still connect a load here, and, you can do, work, right? It's just a matter of convention, okay? It's just a matter of convention. Just like it is in this case, right? In the gravitational case. Okay, so that's just like a quick explanation of voltage and ground. Or actually, let's not erase that. Now, let's sort of try to understand what about current? What is current, okay? And, current, really you're gonna get into this. You're gonna learn like an electromagnetic version of Ohm's law in EM next year, which is really cool. Basically, and so current was a bit of a mystery to me until I took that course. Literally, what current is just you have a plane, okay? Let's you have this imaginary plane, okay? And then you have charged particles, and going through this plane, right? And literally, what you're doing is you're just measuring how much charge is going through this plane per unit time. So what is the speed of charged particles that move through this plane per unit time? Okay, and so in the mechanical circuit, that would just be the flow rate. Okay, so how much water is flowing through like let's say put a net through the pipe. How much water flows through the pipe per unit time? Okay. And so that's what current is. And before we continue, let's just go back. Let's just sort of try to understand these units a little bit better. I realize I probably should have mentioned that earlier, but we'll mention it now. So voltage is units of joules per coulomb. Okay, so joules per unit charge. Okay, so in gravitational terms, it's not. I lied a little bit. It's not exactly analogous to gravitational potential energy. It would be more analogous to gravitational potential energy divided by mass. So potential energy per mass unit, which is actually, which is actually if you think about it, that's exactly just height, right? So because in so GPE is if that's equal to mgh, when divided by m, that would be basically just height multiplied by the gravitational multiplied by gravitational acceleration. So that's what voltage is basically analogous to. It's literally just like you can just think of it as height in a circuit, right? And ground is just where you decide to be zero meters. It's where you decide to measure your height from. Okay. And then charge, or sorry, not charge. My bad. Current. The units of current are in coulombs per second. Okay, so it's just how much charge it's flowing measure charge through coulombs. How much charge is flowing through this plane, right? Per second, okay? Charge per second. And I hope that explains, you have a better conceptual understanding of what voltage and current are. And I'm going to sort of try to, challenge your understanding of that a little bit. So I'm going to draw a circuit. I'm going to ask you a question. Pause the video, think about it, and then we'll try to, I'll work through it, okay? So, let's say you have a circuit like this, okay? I have a voltage source. And I have two resistors in parallel. Okay? I have two resistors in parallel. Good enough. And my question to you is, okay, so let's say, I don't know, this is, at a certain voltage. Which resistor will have more voltage flowing through it, or across which resistor will the voltage be higher, R1 or R2? I want you to pause the video and think about this. Okay, does R1 have a higher voltage through it, or does R2 have a higher voltage through it? Okay, so the way to think about this is with that mechanical analogy I was mentioning earlier, right? Okay, so let's think about this mechanically, right? We have the water flowing, right? And when it's getting pumped up to a certain height, okay? The water is, flowing, it's getting pumped up to a certain height, okay? Let's say you're a water particle, you get pumped up to, let's say the height is like 10 volts, 10 meters, right? Interchangeable, 10 volts, okay? Your water particle, you get pumped up to 10 volts, okay? The height throughout this entire node of the circuit is going to be the same, right? So the voltage through R1 and R2 is going to be the exact same because they're both pumped up to the same sort of potential energy, right? The height of the water molecule is the same here through R1 and through R2. This height of like 10 volts or 10 meters is the exact same. Conversely, what would happen if, instead of putting them in parallel, what would happen if we put them in series then, right? So if we put them in series, as you've probably already, surmised, we get the exact opposite scenario, okay? So the water molecule, in our analogy, the water molecule is flowing. It's at this height of 10 volts, or 10 meters, let's say, and it's at this height of 10 meters, and then it flows through this R1, and then look, now it's at like a lower height, right? It's at a lower height. I don't know. Let's say, we'll figure out how to quantify this exactly depending on the resistance values, but let's say it's at 5 meters, and then it goes through, and it goes to even lower height. Now it's at 0. Now it's at ground, right? So in this case, the voltage is being, the voltage through these two resistors is not equal, and they're in series. And what we have is a voltage divider. This is a voltage dividing circuit. All right, now that we've figured out voltage division, conceptually, we're gonna get into the math a little bit later. How about, let's say you have a circuit like this, okay? And you have a current source in this case instead. Is this going to split up the current, or is the current through both of these branches, both R1 and R2, going to be the same? Let's think about that. So in this case, you can imagine if it's water flowing through a pipe, right? We have a bunch of these water molecules flowing through a pipe, and there's a split in the pipe here, right? Some of the water molecules have to go this way, and some of the water molecules have to go that other way. So there's going to be less water flowing through the pipe than there was, flowing out of the source, right? So in this case, we do have current splitting. The current is divided. In this case, since we have both the current source and the resistors in parallel, the current is divided. And so obviously, analogously, if you have a circuit like this, if you have a circuit like this with the two resistors in series, then you're not going to get current division, okay? All right. This is not a current dividing circuit. Okay. So now let's explain this a little bit more formally, and we'll figure out how to quantify this effect with a voltage divider. Okay. All right. So let's say we have a voltage of 5 volts, and we have two resistors, R1 and R2. Actually, how about we pick a little bit nicer numbers? Let's say this is 12 volts, okay? And now the R1 value, let's say R1 is equal to 1 kilo ohm, and R2 is equal to 3 kilo ohms. Okay. We want to measure the voltage here. At this point in the circuit. My question to you is, at this point in the circuit, we know this is first of all, we know this is a voltage dividing circuit, okay? We know the voltage here is not going to be 12 volts, it's going to be less than 12 volts. Is it going to be, at this point in the circuit, is it going to be, is more than half of the voltage, will more than half of the voltage have been sucked up by that R1 resistor? Or will we have the majority of the voltage still left at this point in the resistor? So will it be more than 6 volts or less than 6 volts? And I want you to think about that, because we have, right now, we have two resistors with different resistance values. Okay. So hopefully you thought about it, and now let's get into the math and see what the answer is, okay? So, we are going to have to use Ohm's law here, right? And it's going to be pretty simple to use Ohm's law. First of all, we're just going to find the equivalent resistance of this, and this is easy peasy for you guys to find the equivalent resistance of. You guys have done really complicated equivalent resistance for circuits. So now we have a 12 volt source, 4 kilo ohm equivalent resistance. We can find the current through the circuit. What's the current through the circuit? We have Ohm's law, V equals IR, right? V equals IR, so I equals V over R. Current equals 12 volts over 4 kilo ohms. And so whenever you have kilo ohms, whenever you have kilo ohm resistances, you have volts on the order of magnitude of like 1 volt. your currents are going to be in milliamps. Okay, so this is like, realistically, when you're building circuits, you're probably going to have kilo ohm order of magnitude resistances and milliamp order of magnitude currents. Okay, so in this case, it's going to be 3 milliamp current. Okay, 3 milliamp current going through this, and now with this 3 milliamp current, we can figure out, okay, what is the specific voltage through R1 and what is the specific voltage through R2. So because we have V equals IR, so V1 for voltage, so V1 here, let's call this V1, is going to be equal to I times R1, and that's going to be equal to 3 milliamp times 1 kilo ohm and 3 volts. So then we're going to have, sorry, I realized this is a bit confusing notation. So then the voltage drop across this resistor is going to be 3 volts, okay? And let's name this differently. I'm going to name this Vx. So then Vx is going to be equal to 12 volts minus 3 volts, which is going to be equal to 9 volts, okay? So this is our final answer, because we have a 3 volt voltage drop across that resistor, right? So then the difference of voltage from the top to the bottom of the resistor is going to be 3 volts. So here you can see that's more than half of the voltage is still remaining, okay? And that's because that 1 kilo ohm resistor, it's a lower resistance than the 3 kilo ohm resistor. So when we look at the ratios, basically there's going to be less voltage going through the R1 resistor than there's going to be going through the R2 resistor, right? Because the voltage drop is directly proportional to the resistance, okay? And so now let's summarize what we just did. Basically, what we had is, in order to find Vx, oops, don't want to read. In order to find Vx, what we did was we had the initial voltage V, which is 12 volts, minus I times R1, right? Minus V1, or let's do this from V minus V1. That's V minus I times R1. I was V over R, and sorry, so this R here is RT, right? What does RT equal? RT equals R1 plus R2. V minus V over R1 plus R2 times R1. We can factor out of V here, so we get 1 minus R1 over R1 plus R2. And 1 minus R1 over R1 plus R2 is, is going to be V times R2 over R1 plus R2. Okay? So in this case, basically, the voltage here is proportional to the voltage at R2 divided by R1 plus R2, okay? The voltage at R2, or sorry, the resistance R2 is higher than the resistance R1. So that's why more than 50% of the voltage is present at this node, right? We can see that reflected in our final expression, okay? And this is the voltage division expression. Now let's move on to current division, okay? Let's go on a new page. Oops, we're on a new page? Okay, current division. So for current division, we're gonna basically draw the same circuit, except we're gonna have a current source instead, right? So we're gonna have a current source. The current source is gonna be 12 amps, or I guess 12 milliamps, right? If we're gonna use realistic sort of order of magnitude. 12 milliamps, and then R1 and R2 are going to be, we're going to use the same resistance values as we did before. I'm just going to check what we used. 1 kilo ohm and 3 kilo ohms, right? So we're going to, I'll draw some blue this time just to differentiate a little bit. R1 equals 1 kilo ohm, and R2 equals 3 kiloohms, okay? Okay, so we have, and I'm going to label all the variables just to be clear from the start. So we have, IT, I total, the big current, going through, going from the current source. And then we're going to reach this node, and the current's going to split up into two different currents, right? I1, I'm going to draw this in a different color. My bad. I realize it's conflicting with the blue for the resistor values. So IT, and then we're going to have I1 and I2, okay? From Kirchhoff's current law, we know that the current going into a junction is equal to the current going out of a junction. Okay, so if you guys remember Kirchhoff's current law, then this is the expression that we have: I2 equals I1 plus I2. And similarly up here, Kirchhoff's voltage law, all the voltage through one loop is going to add up to 0. Okay, so that means 12 volts is equal to the voltage. A 12-volt voltage increase is going to be equal to the sum of the voltage drops through these two resistors. That's where I got that from. Just to be perfectly clear, bringing this back to KVL and KCL, which are very important for you guys to really understand and know. We know this. So then my question to you is, again, same thing as before. Which of these currents is going to be bigger? Is I1 going to be the bigger current, or is I2 going to be the bigger current? Let's figure this out the same way we attacked the previous problem. So again, we're going to find the equivalent resistance, and that shouldn't be too difficult. So I apologize for picking maybe not the best numbers, but we're going to add but when we add these when we add these two resistors up in parallel, what we get is the following resistance. And what we get is so we have 1/1 plus 1/3 all divided by 1, and that's going to be 0.75 kilo ohms, so 0.75 kilo ohm resistance. Okay, and then we're going to apply Ohm's law to this circuit. Of course, Ohm's law, we have V equals IR. So then if we're trying to find the voltage of the whole circuit, and as we went through, right, the voltage through both of these branches of the circuit is going to be the same, because you can think of it literally, the water molecules are both at the same height, right? So V equals IT times RT. I'm going to call this 0.75 kilo ohms RT, okay, just like R total, or R equivalent, I guess. And so that's going to be 12 milliamps times 0.75 kilo ohms. That ends up being 9 volts. Okay, so we have 9 volts basically at or like a height of like 9 meters, you can think, at the top of the circuit. And then in order to find the current I1, we again I1 equals V over R1. Okay, so then 9 volts over 1 kilo ohm. 9 volts over 1 kilo ohm is going to be 9 milliamps. Okay, all right. So as you can see here, 9 milliamps. That's more than half of this 12 milliamp current. Okay, so that means we have more current going. We have more current going through I1 than we have going through I2. Okay, and that's in contrast with the voltage dividing circuit. Okay, in the voltage dividing circuit, we had a smaller voltage drop over R1 than over R2. The smaller resistor led to a smaller voltage drop. The larger resistor had a larger voltage drop. In this case, it's the opposite. The smaller resistor has a larger current through it, and the bigger resistor has a smaller current through it. Okay, and that's because current is inversely related to resistance, right? As opposed to voltage being directly proportional to resistance. Okay, so that's reflected in Ohm's law. And now let's finally get this into a nice formula, just like we did last time. What we're going to do is, how do we figure out I1? Well, let's just expand this out, right? I1 equals V over R1. So, whoops, still on highlighter. That means I1 equals IT times RT over R1. So RT, of course, right? So I'm just gonna expand this out on the side real quick. 1 over R1 plus 1 over R2, right? That's just from your figuring out how to, find the equivalent resistance for parallel resistors. You guys know how to do that. So it's going to be equal to IT times 1 over R1 plus R2, okay, times 1 over R1. I'm just going to move that R1 into the denominator, times 1 over R1, oops, sorry, my bad, 1 over R1 plus 1 over R2, right? R1 times 1 over R1 plus 1 over R2. If we do that, we get 1 over 1 plus R1 over R2. 1 plus R1 over R2 is going to be R2 plus R1 over R2. Let's just flip this around. And finally, what we get is this. I1 equals R2 over R1 plus R2. If we wanted to find I2, then that's just going to be I total times R1 over R1 plus R2, okay? So it's just whatever is the opposite of the current you want to find, okay? And that's the current division, voltage division formulas. Just one more quick thing. We went over a conceptual explanation of voltage and current and resistance. It's less warranted to go through a bit of a ramble about resistances, but just quickly as an addendum to this video, which is already getting quite long, I just wanted to mention a resistor. You can really think of it as a machine that turns a voltage into a current or current into a voltage, okay? Because we can have a circuit that has a voltage, okay, but no current, okay? So this has these two wires have a voltage across them, but because it's an open circuit, there's no current, right? Or if we have if we have a short circuit, then we have a current going through the circuit, but then the voltage at both the points is going to be the same, right? There's no voltage drop. So you can have a voltage drop of 0, or a current of 0, and then you have to introduce a resistor in order to turn that voltage into a current or a current into a voltage. So that's another way we can think about resistors. And it was a bit of a longer video than expected, but hopefully that clears some things up conceptually for you. And I'll see you guys soon.